Okay, I'm going to do another quick little video solution here to Module 1, Lesson 4, Review, Part 1. So here we want to look at, we're showing two tables, a function and its inverse. We're supposed to just enter the missing numbers in order. I'm just going to do one of these because they're all pretty much the same. There's several problems like this on the assignment. All we're doing here, we realize that when we take a function and we produce its inverse, we're just exchanging the domain and the range. So essentially just switching x and y values. So for this point right here, which started off with an input of -1 and an output of -5, the inverse is going to have an input of -5 and an output of -1. Let's see, the next spot down here, we've got these ordered pairs correlate in the function and the inverse. So input of 4 gives an output of 2 with the function. So in the inverse, 2 becomes the input, 4 becomes the output. And then finally down here at the bottom, originally 5 is the input, 7 is the output. So in the inverse, 7 is the input and 5 is the output. Same kind of thing. I'm going to skip that. Same kind of thing there. I'm going to skip that. Okay, this question, it gives us a relation consisting of a set of 5 ordered pairs. We want to determine whether the above relation is a function or not. Well, it's going to be a function if it meets the criteria for a function or passes the function test, which just says each input maps to exactly one output. So let's look at the input values: -7, -3, -2, -1, and 4. Those are all different input values, and so therefore each input is going to produce only one output. So that is a function. Let's write the inverse of this function. So I'm just going to reverse the x and y values for each of these ordered pairs. So the first one becomes -9, -7. Going to put commas between each one. Next one becomes 8, -3. Next one becomes 9, -2. Next one becomes 7, -1. And last one becomes -6, 4. Okay, so now we want to determine if that is a function, if the inverse is a function. So we'll look at the inputs and see if each input produces exactly one output. So we have inputs of -9, 8, +9, 7, and -6. Those are 5 different input values, so each one will only produce one output. So it is a function. Okay, another one, similar problem. This time we can see, when we want to determine if the above relation is a function, we can see that an input of 0 produces outputs of both 4 and 9. So that means it is not a function. It fails the test. What about the inverse? Let's flip around the x and y values. So the first ordered pair becomes -6, -1. Second becomes 4, 0. Third ordered pair, 9, 0. Fourth ordered pair, -2. Whoops. -2, 7. Last ordered pair, 2, 9. Okay, so let's see here. This time it looks like for the inverse, the input values are -6, 4, 9, -2, and +2. Those are 5 different input values. So for the inverse, each input produces only one output. It does not matter that the input 4 produces an output of 0 and the input 9 produces an output of 0. The fact that those y values are the same is irrelevant. All that matters is that each input value produced only one output value. So there are not, for example, multiple ordered pairs that have an input of 4. So that is a function. Okay, look at one more here. This time it looks like we have inputs of -7, -1, 0, 3, and 4. So that is a function. The inverse is going to have ordered pairs -8, -7. Next one is 4, -1. Next is -7, oops, -7, 0. Next is -8, 3. And next is -1, 4. So this time it looks like we have overlapping input values. -8, and -8 appears twice in our inverse as an input. An input of -8 produces -7, and it also maps to 3, so the inverse is not a function. Okay, now we're just looking at looking to see which of these graphs represents an inverse. So which are graphs of an inverse? We know that the graphs of inverses have symmetry about the line y equals x, so the diagonal line y equals x. Okay, this almost looks like it at first, but we can see that it's not really. It appears to instead be maybe like a rotation about the origin or something, but the red line and the blue line are not reflections about the line y equals x. Different for a different reason. This next option does not represent graphs of inverses. These are reflections about the line y equals -x. That's the wrong line. Next option, these are reflections about the y-axis, so that's also not an inverse. Next option, we have reflections about the x-axis, so that also fails. And then finally, the last option, we can see these are reflections about the line y equals x. So that last option shows a graph of inverses. Okay, same thing again. For the same reasons, we can see this first option is, only one is going to be the correct option. So let's just find the one that does. Let's find the one that appears to have symmetry about the line y equals x. Well, there it is right there. We can see that the red and the blue are reflections about that diagonal line. So that's the correct answer. Okay, got it right. Okay, the last two questions, I think these are kind of good questions myself. These ask you to take a relation that consists of a set of 4 ordered pairs, and we want to see for which of these options could we pick a point that would generate, when we add it to the original set, it would create a relation that is a function, but an inverse that is not a function. So in other words, we need to, if the original relation is going to be a function, each input value is going to still have to produce its own separate output value. So for each input, there's one output. The first option does that. So let's check it for the moment and see why it does that, and then we'll do the second test in a moment and see if it also works for the inverse. So in this case, an input of 3 is different than -3, 1, 4, and 5. So that means that it works that the original relation is a function because each input produces exactly one output. Now we want the inverse to not be a function. So that would mean that 5, the input of 5, would have to overlap with one of these, which it does not. So that is not a good choice because the inverse is not a function and it needs to be. Okay, the next one fails because the input of 4 is already represented with the relation. So if I chose that point, then this point would have an input of 4 and an output of -2, and this one would have an input of 4 and an output of -8. Doesn't work. An input of 4 would produce 2 outputs. So the original relation would not be a function, and it needs to be. Next one. Also doesn't work. This time an input of 5 overlaps with the input of 5 on this fourth point. So for the same reasons, that option fails as well. Okay, it looks like the next one is going to work. Let's see why. -4 is a different input than each of the other 4 inputs. So that means that the original relation would be a function. Each input produces exactly one output. But when we flip the points around, you can see that this point right here, when we reverse the x and y values, is going to have an input of -6 and an output of 5, and this point would have an input of -6 and an output of -4. So after reversing x and y, an input of -6 would produce 2 separate outputs, which means it's not a function, and that's what we want. We want the inverse to not be a function. So that one works. Next one also works for the same reason. 0 is different than each of the 4 inputs for the relation, so that makes the relation a function, but 4 overlaps with one of the y values. So when I flip x and y, the input value of 4 will produce an output of -3 and an output of 0. So once again, the inverse will not be a function. So that works. For the same reason the last one works. Oh, no, it doesn't. Never mind. It doesn't work because an input of 1 already exists. And so if I chose that point, for the relation, an input of 1 would produce both an output of 9 and an output of 4, which would make it not a function. But we want the relation to be a function. So that one fails. So those are the only 2 answers that work. Okay, another one just like this. This time we want to be able to pick a 5th point so that the new relation is not a function, but the inverse is a function. So -7 already exists as an input, so that's good. That means that for the relation, an input of -7 produces 2 outputs, so that's good. That means the new relation is not a function, but what about the inverse? If I pick this point, then 9 is a different y value than each of the original y values. So when I flip all the x and y values, then each x value in the inverse will only produce one output. So that does work. It meets both criteria. What about the next one? 2 overlaps with an x value, so that's good. That means that the relation is not a function. And -2 is different than each of the current y values. So when I flip x and y, that means that the inverse will be a function. So that one also works. What about 2 and -1? For the same reason, that works. We can already see that 2 works. And -1 is also different than each of the original y values, so it works also. -7 overlaps with an x value, so that means that the first criterion is met. The new relation is not a function because -7 would map to both 3 and -9. However, when we flip the x and y values, we can see that an input value of 9 in the inverse would map to -7 and also to 0. So the inverse would not be a function, so that one fails. Next one, 7 is different than each of the x values, and -6 is not. So that means that the relation would be a function, but the inverse would not, and that's the opposite of what we want. So that one fails. And then finally, negative 9, 9 fails because in this case, the x value is different than each of the original x values, and so is the y value different than each of the original y values. So both the relation and its inverse would be functions, which is not what we want. So these are our answers.